Sam!
Hey, Sam!
Forget it. Hey, Sam! Why are you working on your laptop? We just got out of school. Are you coming out?
No thanks. I want to stay home and study quadrilaterals on my computer. I need to find out their properties.
Why do you want to know about quadrilaterals?
Didn't you know? They've just launched a competition to design an ideal country club for Hong Kong to promote tourism. I'm entering in the junior category.
Oh yes, I did hear something about it.
I want mine to be different, so I want to use various quadrilaterals in the design.
But quadrilaterals? What's so special about quadrilaterals?
Nothing if they're general quadrilaterals. A general quadrilateral has no particular relationship between its sides or between its interior angles.
That's true. If a quadrilateral does have a relationship between the interior angles or the sides, it can be a trapezium, parallelogram, rectangle, square, rhombus, or kite. All these shapes would look great in your design.
When I was small, I liked to draw houses, like this drawing. I drew them using all kinds of quadrilaterals.
Hey, look at this house here. Do you see its shape? Its side view is a trapezium.
You're right. A trapezium is a quadrilateral with a pair of parallel opposite sides. In this quadrilateral ABCD, AB is parallel to DC, so ABCD is a trapezium.
Of course. What's more, these two lines are parallel, and these are transversal of the parallel lines, which means these four angles are...
I know! It's the theorem that says the interior opposite angles of parallel lines are supplementary.
Therefore, the sum of angle A and angle D is 180 degrees, and the sum of angle B and angle C is also 180 degrees.
There you are, the properties of a trapezium.
Look at the drawing. The roof of the house is a parallelogram.
Really?
When two pairs of opposite sides of a quadrilateral are parallel, the quadrilateral is a parallelogram.
That's right. And have you noticed that a parallelogram can be divided into two congruent triangles? You see? As alternate angles of a pair of parallel lines are equal, it follows that these two triangles are congruent. These two triangles are also congruent. Since corresponding sides and angles of congruent triangles are equal, the properties of a parallelogram are: opposite sides are equal. That is, AB equals DC, and AD equals BC. Opposite angles are equal. That is, angle A equals angle C, and angle B equals angle D.
Ah, so that means for parallelograms there's no relationship between the lengths of adjacent sides.
That's not all. We can also use the rules for proving that triangles are congruent to prove that triangle ODC and triangle OBA are congruent. As corresponding sides of congruent triangles are equal, this means that OA equals OC and OB equals OD. This gives us another property of a parallelogram. Its diagonals bisect each other.
We can also use the properties of a parallelogram to solve some geometrical problems. For example, in this parallelogram, ABCD, it's known that angle DAC equals 2A plus 10 degrees. Angle CAB equals 50 degrees. Angle DCB equals 140 degrees. Also, AD equals 5x minus 6 centimeters. BC equals 9 centimeters. OA equals 2x plus y centimeters. And OC equals 3x plus 2 centimeters. So what are the values of A, X, and Y? The answer is A equals 40 degrees, X equals 3, and Y equals 5. Many houses and other buildings in the picture are all in the shape of rectangles. Also, look at the doors and windows here. They're all rectangles too.
Hey Sam, can you give us the definition of a rectangle? Then we can go on and study its properties.
Okay. This drawing instrument's a pantograph. Now, a rectangle is a type of parallelogram. If a parallelogram has an interior angle of 90 degrees, then it's a rectangle. Since the interior opposite angles of a parallelogram are always equal, the four interior angles of a rectangle are right angles.
Therefore, it has all the properties of a parallelogram.
That's right, and a rectangle has other properties such as the diagonals are equal. For these two right-angled triangles, we can use the SAS rule to prove that triangle ADC and triangle BCD are in fact congruent. It follows that AC equals BD.
As the diagonals of a parallelogram bisect each other, so the diagonals of a rectangle bisect each other, forming four equal segments.
The fence around the house is made up of rhombuses.
That's right. I copied the shape from a wattle fence at the bottom of the garden. That's why the shapes in my drawing are all rhombuses.
You know, a rhombus is a kind of parallelogram too. It has two equal adjacent sides. Since the opposite sides of a parallelogram are equal, so a parallelogram with four equal sides is a rhombus.
A rectangle's four interior angles are right angles, but adjacent sides are not equal. A rhombus's four sides are equal, but its four interior angles are not right angles.
So a rhombus is another parallelogram, except that the diagonals of a rhombus bisect the interior angles. In this rhombus, we can use the SSS rule. This will prove that triangle CED is congruent to triangle CEB. It follows that angle DCE equals angle BCE, and so on. Therefore, each interior angle is bisected by a diagonal. Furthermore, the two diagonals of a rhombus are perpendicular. Look at these congruent triangles again. Angle CED equals angle CEB. So each of them equals half a straight angle, which is 90 degrees. Therefore, CA and DB are perpendicular to each other. Look at this geometrical problem. BCDE is a rhombus. It's given that angle DEC equals 40 degrees. So what is the value of angle ABE, an exterior angle of the rhombus? Do you use the relationship between an exterior angle and the interior opposite angles of a triangle?
Besides rectangles, the windows were also drawn as squares. A square is another particular example of a parallelogram. When a parallelogram has a pair of equal adjacent sides and includes a right angle, it is a square. According to the properties of a parallelogram, the four sides of a square are equal, and the four interior angles are right angles.
Say, look here, did you know that between a square, a rectangle, and a rhombus, there's a special relationship?
Oh, a square satisfies a rectangle's condition that interior angles are right angles. The square satisfies a rhombus's condition that adjacent sides are equal, so it's a combination of rectangle and rhombus. A square should therefore show all the properties of both a rectangle and a rhombus. The two diagonals of a square are equal, perpendicular to each other, and bisect each other, forming four equal segments. Since the diagonals bisect the interior angles, the angle formed between a diagonal and its adjacent side is 45 degrees.
You did well. You've understood the interrelationship among shapes and their properties.
Yeah, I'm impressed.
Now then, another geometrical problem. ABCD is a square. It's known that triangle AQD is an equilateral triangle. So, what is the value of angle QBA? I'll give you a few hints. What's the value of the interior angles of equilateral triangles? Is triangle ABQ an isosceles triangle? What are the characteristics of base angles of isosceles triangles? And don't forget, ABCD is a square. Since triangle AQD is an equilateral triangle, it follows that angle DAQ equals 60 degrees. ABCD is a square. This means that angle DAB equals 90 degrees. Therefore, angle QAB equals 90 degrees minus 60 degrees equals 30 degrees. Furthermore, as they're the sides of a square, AB equals AD. Therefore, AB equals AQ. This means that triangle ABQ is an isosceles triangle. According to the rules governing the sum of interior angles of triangles and the properties of base angles of isosceles triangles, angle ABQ equals 180 degrees minus 30 degrees divided by 2 equals 75 degrees.
Hey Sam, I noticed that in the picture there was a boy flying a kite. Is it you?
No, when I was young I really liked kites a lot, but we lived near the airport then, so I couldn't fly them. So I included my dream of flying kites in the drawing.
Your drawing has made me think of something. A kite is a quadrilateral. It's not, however, a parallelogram. For a quadrilateral ABCD, if there are two pairs of equal adjacent sides, that's to say if BA equals BC and DA equals DC, then ABCD is a kite. One property of a kite is that one of its diagonals is an axis of symmetry. Using the SSS rule, it's simple to demonstrate that triangle ABD and triangle CBD are congruent. Also, using the SAS rule, we can demonstrate that triangle ADE is congruent with triangle CDE. Therefore, another property of a kite is that the two diagonals are perpendicular to each other.
I just thought of something. When we know the quadrilateral, then we're sure about its properties. But can we be so sure in reverse? See, if we're only given the properties of a quadrilateral, can we be certain which quadrilateral is denoted by those properties?
You're right, that's a good question. Let's take the example of a parallelogram. Like here, a quadrilateral, WXYZ. If we know only that its two pairs of opposite sides are equal, that is, WX equals ZY and WZ equals XY, then can we definitely say this is a parallelogram? Using the rule SSS, we can further demonstrate that triangle WYZ and triangle YWX are congruent. It therefore follows that angle WYZ equals angle YWX and angle ZWY equals angle XYW. This means alternate angles are equal. Therefore, WX is parallel to ZY and WZ is parallel to XY. If we compare these findings with the definition of a parallelogram, we find that WXYZ is in fact a parallelogram.
Oh, right! I'll try it with other properties of quadrilaterals to see if they fulfill the conditions for identifying a particular type of quadrilateral. Why don't we work together?
Good idea! With my newfound knowledge of the various quadrilaterals and their properties, I'm sure I'll have lots of new ideas for the design of my country club.